Build skills with experts anytime, anywhere. Get certified, get ahead. The world's largest selection of courses, affordable online courses and learning opportunities, top categories.
The building blocks of Hadoop. The Hadoop Distributed File System HDFS for storage, the MapReduce programming model for processing, and finally the Resource Negotiator YARN for cluster management. This will help you bridge the gap between plain vanilla programming and big data analysis. Learn how to set up a pseudo-distributed Hadoop environment and submit and monitor tasks on that environment using the built-in web interface. And finally, understand the configuration choices you can make for stability, reliability, and optimized task reduce the programming model. And finally, YARN, the manager of resources. In this module, we'll try and understand why is it that we need a distributed computing environment. The sheer amount and scale of data that we deal with to solve problems requires this. We'll see the role that Hadoop plays in a distributed computing setup and also take a brief look at technologies which work along with Hadoop. It's often helpful to have numbers in order to get an understanding of how big is big data. We look at Facebook, the NSA, and Google and see how much data they deal with. Facebook currently stores 300 petabytes of data. 1 petabyte is 10 raised to the power 15. That's more zeros than you know what to do with. It processes 600 terabytes of data a day. Terabytes is 10 to the power 12. The number of users that log into Facebook per month is 1 billion. There are 2.7 billion likes per day. When you click on like, you're one amongst 2.7 billion in a day. And finally, 300 million photographs are uploaded to Facebook in just a day. We look at equivalent stats for the NSA. Stats for the NSA, you have to realize, are not accurate because the NSA obviously doesn't release them. People deduce this from various pieces of information they have. The NSA currently stores roughly 5 exabytes of data, that is 10 to the power 18. The processing of NSA is a little lower, roughly 30 petabytes. The NSA is set to touch more of the internet than Google does. 1.6% of the internet traffic per day passes through the NSA in some way. All your web searches, the website that you visit, phone transactions, health information, financial records, everything, legal information, Skype calls, all of these are potentially monitored by the NSA. What about Google? As you can imagine, the amount of data stored by Google beats the two organizations we've seen so far. It stores 15 exabytes. Google's core job is to download the entire internet, so this shouldn't seem surprising to you. It processes 100 petabytes of data, which also makes sense. It's constantly downloading new web pages which are updated and processing them for search results. It has indexed 60 trillion web pages, serves over 1 billion users in a single month. This is only for its search property, and serves 2.3 million searches in 1 second. That is a huge data set. Each of these organizations deal with a data set which would have been unthinkable even 10 years ago. Now, if you think about a data set like this, do you really think a single machine will be able to service this? However powerful that single computer is, it just cannot deal with data at this scale. Now, that's a very blanket statement. It can't deal with data. Let's break it down and see what is it that we require of a big data system. It should be able to store massive amounts of data because the raw data itself is huge. So there's storage. We should be able to extract useful information from this millions and billions of rows of data. So we need to process it in a timely manner. And finally, there is a third requirement which may not be obvious. It is obvious though if you look at the trend in data usage by companies like these. We'll take an example of LinkedIn. LinkedIn grew from 37 million users from the first quarter of 2009 to over 450 million users today, currently in the middle of 2016. Now, to keep up with data that grows at this rate, you need a special kind of system. The infrastructure itself should be flexible such that as data grows, you can increase storage and you can increase computing capacity without completely reworking your system. Any big data system that you build needs to scale. Storage and processing capacity are useless without the ability to grow them as data grows. Big data system requirements cannot be met by traditional technologies. They don't cut it anymore. In order to get all the characteristics that we require from our system, we need a distributed computing framework. And this is where Hadoop comes in. Any system which performs computations for us can be built up in two ways: a monolithic system, where everything is on a single machine and in one big chunk, or a distributed system, where there are multiple machines and multiple processes which run on these machines. In exactly the same way, there are two ways to build a team. For example, a basketball team. Your team can have a star who probably dribbles and shoots. So you have one star who does the heavy lifting, or an entire team of good players, none of whom are stars, but all of them work together really well and are really good at passing the ball. This is the exact equivalent of a supercomputer or a cluster of machines, which are typically commodity hardware and which can be used to parallelize tasks. Two ways to build a system. The monolithic way is the equivalent of one star player that you rely on. That one player does everything. A monolithic system typically is a single powerful server. And if you want more computing resources and capacity from this server, you might be tempted to pay twice the expense to improve the performance of this machine. But you will get less than two times the performance. The performance of a single machine does not scale linearly with cost. On the other hand, if you look at a distributed system, the equivalent of a team of good players who know how to pass the ball and work together really well. Here, the onus of improving performance does not lie with one single machine. It lies with all the machines which work together. The players on this team, the individual machines, are called nodes, and the entire system is called a cluster. No individual node in this cluster of machines is a supercomputer. They all tend to be cheap machines or commodity hardware, but they come together as a team to solve your data processing needs. Something that is axiomatic today but wasn't really well known 15 or 20 years ago is the fact that a cluster of machines can scale linearly with the amount of data that you have to process. The capacity of such a cluster increases with the number of machines in the cluster. If you double the number of nodes that exist in this system, you'll get twice the storage. That's pretty obvious. Each machine comes with its own hard disk, and doubling the number of machines doubles the storage capacity. What makes such a distributed system cool is that you can achieve computational capacity or performance that is twice what you originally had. When you double the number of machines, you get nearly twice the performance, twice the speed. A distributed system satisfies the third critical requirement in big data processing, keeping up with the ever increasing amount of data that we have to process at any point in time. And this is a reason that companies such as Google, Facebook, Amazon, Microsoft build these vast data centers that are populated with hundreds of thousands of machines. These server farms, all these machines which live in these server farms, are where the actual processing of data takes place in parallel. Now, we need something in order to have all these machines work together in a concerted way to solve a single problem. These servers need to be coordinated, and it is a software which will perform this coordination. This is a special piece of software which takes care of the needs of a distributed system. Things like partitioning data so that any data is stored across multiple nodes in a system. This data is protected against loss by replicating the data on more than one node, or coordinating compute tasks. You might have a task which runs in parallel on multiple machines. This software will ensure that all these processes run through to completion successfully and store their results in the correct place. It also needs to handle fault tolerance and recovery. Each individual machine isn't a great system by itself. It's commodity hardware, which means it's prone to failures. Disk failures, node failures, all of these need to be handled. In order to run a process, this software needs to ensure that a particular node has the resources required for the process to run in terms of memory, compute capacity, hard disk space, etc. Distributed computing, which coordinates so many machines together to achieve one objective, adds a huge overhead and complexity to any processing task. Individual developers who work on this distributed system cannot focus on the nitty gritty of the actual cluster management. That's where the software comes in to abstract developers away from the details. Working with distributed systems requires special software whose explicit purpose is to coordinate and manage all the processes and machines which exist within the system. Back in the early 2000s, as Google web search got more and more powerful, Google realized that traditional software, traditional methodologies would not work for the scale of web search. That's when they realized that they'd have to build something of their own to manage all these processes which run on hundreds of thousands of machines. Google developed proprietary software to run on these distributed systems. What were the objectives of this proprietary software? The first was to store the millions of records across multiple machines. So, keeping track of what record existed on what node within the data center was one part of the problem, which this software had to solve. The second part was, how do we run processes across all these machines and coordinate these processes in such a way to achieve a single objective? This was the most important problem that Google engineers worked on back in the day. And they came up with two systems to solve this. One was called the Google File System, and the other was called MapReduce. Google File System was responsible for storing data in a distributed manner. It was a file system which existed not on a single machine, but on multiple machines which made up a cluster. This is the distributed storage problem. MapReduce was used to solve the second problem, the problem of distributed computing, running processes in parallel across multiple machines to take advantage of the inherent parallelism in data crunching tasks and bringing the results of these processes together to achieve something useful, such as lightning fast search results. Google engineers developed these technologies and then published papers talking about how these help in distributed computing. These papers were, of course, available to all other engineers who had been working on similar systems. Engineers working on a distributed computing framework called Nutch adopted these principles based on the published papers from Google and developed the core of what is today Hadoop. The equivalent of the Google file system is HDFS, and the equivalent of the MapReduce programming framework that Google has is called MapReduce. HDFS is the Hadoop distributed file system. MapReduce is the programming model for parallel processing. HDFS plus MapReduce gives us the Hadoop that we know today. HDFS is the file system which manages storage of data across machines in a cluster. MapReduce is a framework to process data across multiple machines. Hadoop is distributed by the Apache Software Foundation and is open source, which means there are thousands of engineers who have contributed actively to Hadoop, and it happens even today. Hadoop constantly undergoes improvements, and in 2013, Apache released a brand new version of Hadoop, Hadoop 2.0. This was a fundamental change where the MapReduce framework responsible for processing data across machines was split into two logical components, MapReduce and Yarn. The responsibility of each of these components was made narrower and more focused. The MapReduce framework was now only to define the data processing task. It was focused on what logical operations you want to perform on the raw data that you have. Yarn was the framework to run the processing task across multiple machines, manage resources, manage memory, manage storage requirements. Yarn did not care what the data processing task was, that came under MapReduce. Yarn only was responsible for running it and seeing it through to completion. These three components, HDFS, MapReduce, and Yarn, have corresponding configuration files. These are the basic building blocks of Hadoop. So, whenever anyone talks about the block diagram of Hadoop, these are the logical components. You have a processing task which you want to run on the cluster which has Hadoop installed. What exactly is the series of steps that happen when you submit a job to Hadoop? The first thing is for you to define map and reduce tasks using the MapReduce API. This is available to work with in Java and also other programming languages. This defines what computation you want to perform on the data. MapReduce programs are packaged into jobs, and the Hadoop cluster deals with jobs as a whole. A job is triggered on the cluster using yarn. Yarn checks whether the cluster or nodes in the cluster have resources in order to run this job. Yarn then figures out where this job ought to be run and then runs the job and stores the data, which is the result of the job, in HDFS, the storage system. This is the typical life cycle of a MapReduce, which is run in parallel across multiple nodes in a cluster. Hadoop and the equivalent Google proprietary system completely revolutionized distributed computing. As distributed computing became more the norm rather than the exception, people realized that the use of Hadoop and the distributed computing environment should not be restricted to hardcore developers in Java. It should be made more democratic. People with different skill sets ought to be able to use the power of distributed computing. This is what led to the rise of a whole ecosystem of tools which work with Hadoop. Some of the most popular technologies that you might have heard of are Hive, which gives a SQL like query interface to data stored on a big data system, HBase, a different kind of database, Pig, a way to convert unstructured data into structured form, Oozy, a workflow management system, Flume and Scoop, tools which allow us to put data into Hadoop and get data from Hadoop. And finally, Spark, a way to perform really cool complex transformations in a functional way on big data. Let's take a brief look at all of these in order to understand where they fit in and how they help make data processing more democratic. Hive is a SQL interface to Hadoop. Traditionally, people from analytics backgrounds are very familiar with relational databases and SQL. But in a big data system, they need to program in Java, which they may not be comfortable with. However, Hive gives a bridge to Hadoop for folks who do not have exposure to object oriented programming in Java by converting their SQL like queries to MapReduces behind the scenes. The user writes queries. What runs in the background is MapReduce programs. As big data systems become more prevalent, people realized that you needed a way to perform low latency operations on your database. HDFS is a batch processing system. HBase was built on top of HDFS to allow low latency operations on key value pairs. Data in HBase can be looked up and scanned very quickly indeed. It's essentially a database built on Hadoop. Pig is a scripting language which allows us to take data in its extremely raw and unstructured form. Think log files where there is absolutely no structure to the data, it's just lines of messages, warnings, etc. It manipulates this data and converts it to a structured format. This structured format can then be stored in HDFS or in Hive and then can be queried by people looking to extract information from it. Pig can essentially take data which looks unusable and convert it to a form which is actually useful. Spark is a technology that's very much in vogue nowadays because of how easy and simple it makes working on big data sets. You can chain and transform huge data sets and extract information with it in a very iterative and interactive way. It's essentially a distributed computing engine built on top of Hadoop. It has an interactive shell, either in Scala or in Python, which allow you to quickly process data sets. You can simply type in a bunch of transformations and see what the result looks like in Spark. It's fast and intuitive, and it has a whole bunch of built-in libraries for machine learning, stream processing, graph processing, all the useful tools that you'll need with a big data system. Organizations like Google, Yahoo, Facebook, etc., don't just run processes of one type. They have a chain of processes constantly munging data. Managing all these processes requires a workflow management system, and that is what Oozy is all about, a workflow management system which works with all Hadoop technologies. If your organization has been around for any length of time, it's likely that all your data lives in a system other than Hadoop. You might want to move this data into Hadoop or move data out of Hadoop into your other system for other processing. Flume and Scoop are technologies which allow you to transfer data to Hadoop and from Hadoop. And with this, we come to the end of this module in our class on building blocks of Hadoop. Hopefully, you've understood why we need a distributed computing system and why it is superior to a single computer setup. You've also understood what role Hadoop plays in a distributed computing setup and why a technology like Hadoop was developed in the first place. You also have some big picture understanding of the various technologies which live within the Hadoop ecosystem and are built on talk about how to install Hadoop, show you how this can be done, and get you started with getting your hands dirty. We'll start off by understanding the different install modes that are available in Hadoop and then install Hadoop first in standalone mode, the simplest of all. The second demo will focus on installing Hadoop in pseudo distributed mode. Hadoop typically runs on Unix or Linux based systems. So if you have a Mac OS operating system or a Linux or Unix machine, you're good to go. Installing Hadoop on Windows is possible, but it's not really widely used, nor is it recommended. I've worked in a bunch of companies which use Hadoop. None of them run it on Windows. All of them use Unix based systems. The installs that you'll see in this module will also focus on Unix systems. Hadoop can be installed in three different modes: the standalone mode, the pseudo distributed mode, and the fully distributed mode. We'll take a look at the characteristic features of each of these modes, starting with the first and the simplest one, the standalone mode. This is the default mode of operation for Hadoop. So if you don't do any further configuration, Hadoop will run in standalone mode. It's the simplest mode. It runs on a single node, that is one machine, typically your local development machine. Standalone mode simply involves downloading all the jar files. Hadoop is built in Java, so has jar files, and running a single JVM process to simulate a distributed system. It uses the local file system for storage. HDFS does not run at all. All file manipulations that you do will be directly on your local file system. Yarn doesn't run as well. There is no negotiation for resources because all that exists is the single node. All the master slave setup that you'll see in a cluster doesn't exist in Hadoop standalone. Standalone Hadoop is extremely useful for testing purposes. If you don't want to go through the entire installation setup and you quickly want to check out to see whether your MapReduce logic is correct, that's when you tend to use standalone mode. If you want to do any advanced level tests, if you want to simulate an actual cluster, that's when you'll use the pseudo distributed mode of your Hadoop install. Now, the pseudo distributed mode lies between the standalone mode and a fully distributed mode on a production level cluster. This once again runs only on a single node, but there are two JVM processes which run in pseudo distributed mode. They simulate two nodes, a master and a slave. The pseudo distributed mode requires some configuration because the other logical components within Hadoop come into play as well. HDFS is used for storage. Some portion of the disk space on your local machine will serve as the HDFS storage, and Yarn also needs to be run in order to manage resources on this Hadoop installation. Pseudo distributed is a great choice when you want a fully fledged test environment. Once again, it's a test environment, but it's approaching how you set up Hadoop in the real world. What we saw were two test environments for Hadoop. The fully distributed mode of Hadoop installation is the production environment. This is how you'd run your MapReduce jobs when they are for real, when they are organization-wide jobs which power your production systems. It runs on a cluster of machines, real distributed computing setup, which serves user traffic. Now, these could be physically different machines, such as Linux servers, which exist in some data center somewhere, or it could be on the cloud. If you were to run Hadoop On Amazon Web Services, for example, you'd have virtual machines which are requisitioned on the cloud. Installing Hadoop in a fully distributed mode for production systems is a non trivial operation. There are lots of configuration parameters which have to be set up just right. This is why we don't manually configure Hadoop on production systems. Typically, we use enterprise editions of Hadoop that's available from a variety of organizations. They package these Hadoop installs in such a way that is pre configured when you run on a cluster of machines. Cloudera, MapR, Hortonworks. These are famous examples of enterprise Hadoop software which are widely used. We'll start off with installing Hadoop in standalone mode. We'll download and unpack the Hadoop jars and then run a test MapReduce to see how it all fits together. Think of this as a preliminary to see how to set up Hadoop in pseudo distributed or fully distributed modes. The first thing to check is to see whether you have Java installed on your machine. Hadoop is built using Java and it requires Java to be installed for you to actually run your MapReduce code and run Hadoop in general. The Java version that I have is version 1.8, that is Java 8. Ensure that the Java version that you have installed is at a minimum Java 7. This is for the latest Hadoop installs. In case you don't have Java installed, I suggest you go over to the Oracle page and download the Java SDK for you to use. Go to this site that you see on the browser and download the Java JDK. JDK stands for Java Development Kit, and it's essentially the software development kit for Java. This has all the Java libraries that you'll find useful and everything that you need to get up and running with Java on your system. Based on the operating system that you're running, choose the correct Java installation. I happen to have a Mac machine, which is why I chose the Mac OS installer to set up Java on my machine. Just follow the steps, set up Java on your machine before moving forward with the Hadoop install. Hadoop jars can be downloaded from the apache.org site. If you type this URL on your browser, you'll find the page for the Apache Software Foundation, which is dedicated to Hadoop. Find a mirror site from where you can download Hadoop. And within there are a whole bunch of Hadoop distributions. I'm going to choose the latest stable version of Hadoop, 2.7.3. Any version of Hadoop 2 should work though. It's when you go to Hadoop 1 that things are really very different. There's no yarn, for example. Click on the tar.gzip file. We don't want the source code, we want the binary distribution, and wait a couple of minutes for it to download. So choose your install directory and remember where you've put it. I've chosen the Hadoop-install directory under my home directory. And there I save it. Once the download is complete, I move to that directory and double click on my tar.gzip file in order to unpack it. Now, double clicking works when you're on a Mac machine. In case you want to do it on the command line, you can simply use tar xvfz and specify the name of the Hadoop tard and gzip file. This should accomplish exactly the same thing, and you have a Hadoop 2.7.3 directory set up under your Hadoop install location. This is the Hadoop distribution directory. Let's explore what's inside this. Under etc, you have the configuration files for the Hadoop environment. Under bin, you have various commands that you'll find useful, including the Hadoop command that you'll see in just a bit. And under the share directory, lives the jars that you'll use when you write your MapReduce job. All the Hadoop libraries live here. Let's go to the terminal and run some Hadoop commands. Go into your Hadoop distribution directory, which is at your install location /Hadoop 2.7.3. The Hadoop command, which is in the bin folder, is what you'll use to run jobs on Hadoop. Jar command that you see highlighted on screen is how you run MapReduce jobs on your Hadoop cluster. We'll be using the Hadoop jar command in just a bit. Our next objective is to run an example MapReduce to ensure that our standalone install works. We'll set up the input files for the MapReduce on the local file system because that's what standalone Hadoop uses. Create an input directory on your local file system. Simply use the makedir command This input directory is where we'll place the input files on which we'll run a MapReduce command. Just copy over files from any other part of your local file system into this input directory. We are just randomly going to choose the files under etc/Hadoop. These are all the configuration files and command files that are present along with Hadoop. We'll use those as text files input for our MapReduce. This is run using the bin/Hadoop command, the Hadoop command in the bin directory. The Hadoop command will be used for other stuff as well, but it's also used to run MapReduces. The second argument is the word jar. This indicates that the MapReduce operation is specified in a Java archive, a jar file, and the jar file that we specify here is one of the MapReduce examples which come along with your Hadoop installation. You don't have to write any explicit code. You can simply use the Hadoop MapReduce examples.jar file. It's a different one based on your version. The jar name will differ based on the version of Hadoop that you've installed. Just change the version number suffix and run one of the existing MapReduces within it. Now, if you simply type this out on your screen and press enter, it'll give you help documentation for how you need to run the MapReduce examples. This jar contains code for multiple MapReduce programs. Our purpose is simply to test our install, so we can pick any of these. The one we are going to demo is the grep program. This is a MapReduce program that counts the number of matches of a regex that you specify as an input argument. Let's go ahead and specify grep, the input directory which feeds to the MapReduce, the output directory where the output of the MapReduce will be stored, and the regex that we want to grep within the input files. Don't worry about all this. We'll look at this in more detail when we come to the MapReduce portion of our course. This is just to give you an understanding of how we can test our MapReduce install. Hit enter. You'll kickstart the MapReduce on your local file system, no HDFS, no yarn, and simply print the output using the cat command present in the output directory. Remember, the output directory has to be a non-existent directory. That is a MapReduce requirement. This will print the result to screen. Notice that all words which start with DFS and their corresponding counts are printed in the output results. This is a MapReduce run successfully on our standalone install. It's now time to set up Hadoop in pseudo distributed mode. This mimics how Hadoop would run on a real cluster. There are a lot of steps here, but before you get started, ensure that at least 20% of the disk space on your machine is available. I have a hard disk size of about 256 gig, and I had to have about 50 gig free before Hadoop would run properly. Another requirement for Hadoop to run on your machine is to have secure shell SSH installed. Check this by running the command ssh localhost. Now, Hadoop in a pseudo distributed mode or in a fully distributed mode requires the master nodes to communicate with the slaves very frequently. This communication is over the secure shell protocol, which is why SSH needs to be installed. In the pseudo distributed mode, there is just one node, that is the one on your local machine. A master slave interaction is simulated by multiple AVMs which run on your local system. In order to ensure that SSH is installed and set up correctly, just try to SSH into your local host and see if it works. Now, this SSH should go through smoothly, like you saw right now on my screen. And this SSH should not prompt you for a password. Hadoop requires passwordless SSH for authentication. Authentication needs to be done using public keys. This is because the communication between master and slave nodes is very, very frequent. We can't add the additional overhead of having a password to log on to SSH. Now, if this just worked as it did on my machine, then you're all set. Your SSH is set up correctly. You can simply exit and you're good to go. If SSH localhost did not work, there can be two reasons for this. The first is that SSH isn't even installed on your machine. If that's the case, if SSH as a command is not found, on your Mac you can fix this by going to System Preferences, Sharing, and enabling remote login. That's all that needs to be done for a Mac. On Ubuntu or Linux and Unix systems, use this command, the sudo apt-get, and install SSH on your machine. There are a bunch of other steps that you need to follow, and this URL at htpcbeginner.com is a good guide to installing and setting up an SSH server on your Ubuntu machine. The second reason why the SSH to localhost may not have worked for you like it did for me was because your SSH prompted you for a password. We need passwordless SSH, and this is only possible if you generate public keys for authentication of SSH. And how do you do that? Using the SSH keygen command. Note this command on screen. Just copy it directly and use it to generate public keys for authentication. SSH keygen is a specific command that you can run to generate a key. We generate a DSA key using the digital signature algorithm. This is a government standard. The DSA that you see in this command indicates that we want to generate a DSA key for the authentication of our SSH, for passwordless authentication. Now, I already have an existing key, which is why this prompts me as to whether I want to rewrite the key that I have existing. Now, if you've never set up a key before, you won't see this prompt. If you already have a key and your SSH did not work, you might want to overwrite the key and move ahead. I choose to overwrite my key here just so you have an idea of the steps involved to generate these authentication keys. Your identity, your public key has been stored in this file. By default, users jananiravi.ssh id underscore dsa dot pub. That's the location of the public key. We'll be using that in just a second, so make note of that location. What we want to do next is to add this key to the list of authorized keys on this machine on localhost. Cat simply appends the key that we just generated in id underscore dsa.pub to the list of SSH authorized keys. This now allows passwordless SSH. Test this by trying to SSH into localhost once again. It should not ask you for a password. And you have passwordless authentication set up on your SSH. You now have Java and SSH set up. Hadoop now needs to be aware of where Java is installed on your local machine before it can function. And this it gets to know by looking at the Java underscore home environment variable. This environment variable needs to point to your Java installation. On a Mac, you can find this installed directory by using the command that you see on screen, user libexec java home. This will tell you the directory location where Java is installed. Run this command, find the Java installed directory. On Ubuntu though, or other Linux and Unix based systems, where Java is installed depends on the operating system that you're using and the version of Java that's installed. It's usually somewhere in the /user lib jvm directory. Find the exact location, make a note of it. We'll be using it in just a bit. Move into your Hadoop distribution directory on the terminal window. Hadoop distribution directory in my case is in Hadoop install Hadoop 2.7.3. All the commands that you run will be typically from this directory. Hadoop has a whole bunch of configuration files which sets the configuration parameter for the various components that run under Hadoop, HDFS, MapReduce, Yarn, etc. There is a specific file for environment variables that Hadoop needs, and this file is present. In fact, all configuration files are present in the /etc Hadoop directory under your Hadoop distribution directory. Here, the first file that we'll be interested in where we set up the environment variable is called hadoop-env.sh. And this is where we'll set the Java underscore home to point to our Java install directly and other environment variables that Hadoop needs. Use any code editor that you're comfortable with in order to make changes to this file. I tend to use Nano because it's built in on the Mac and I know it's always available. Just nano hadoop-env.sh and let's add in those environment variables that we need. You can study what else exists in this file. At the very bottom, add in the Java underscore home environment variable by using the export command. Remember, you should point it to where your Java is installed. It'll be different based on the machine and the version of Java that you're using. Also set up the Hadoop underscore prefix environment variable to point to your Hadoop distribution. This is another variable that Hadoop requires to start up and run in pseudo distributed mode. Now to save this file and exit. In Nano, I use Control X to exit. It'll ask me if I want to save the current changes in my file. I answer Y for yes. It'll then confirm the name of the file that I want to save it as. Hadoop-env.sh is correct. And then go ahead and save it. I now have my environment variables set up. For the standalone mode, we did not configure any of the individual components of Hadoop. For the pseudo distributed mode, we do need to set up some configuration parameters, and we'll have different XML files where we add these configuration properties. Each of these XML files correspond to one component in Hadoop: HDFS, yarn, or MapReduce. There is also a core site.xml, which is what we'll start with, which is the configuration common across Hadoop. It's not a component specific configuration file. Open up core-site.xml in your favorite text editor and then set properties you want within the configuration tags that you see there. The fs.defaultFS property points to what file system we want to use with Hadoop. We want to use HDFS, and it can be accessed on your local host at port 9000. Let's move on to other configuration files. Let's configure HDFS itself. This has its own configuration file called hdfs-site.xml. All of these files, note, are in the etc/Hadoop directory. In the HDFS configuration file, set up the replication factor to be 1. Replication is a way by which fault tolerance and recovery is built into Hadoop. Any data that you store within HDFS is stored on more than one machine in the cluster. If a single machine goes down or its disk is lost or corrupted, you don't lose your data because it has been replicated to other machines. Because we are running in pseudo distributed node, which has only a single node, the replication factor has to necessarily be 1. The next component that we configure is the MapReduce framework on Hadoop. Now, the mapred-site.xml did not exist in the default installation that I had of Hadoop 2.7.3. Create the file if it doesn't exist. I've created a new file, mapred-site.xml, and set up a configuration property indicating the resource manager or the resource negotiator that our MapReduce framework is going to use. I've specified it to be yarn. Other valid values for this are local, classic, but we've chosen to use yarn. What does this MapReduce framework name really do? This framework name specifies how you want to negotiate for resources on the cluster. In this case, we want to use yarn as our resource negotiator. We don't want to use classic, which is typically used only for the first version of MapReduce, and we are running version 2. We don't want to use local, which is used for running MapReduce locally, like in standalone mode. For pseudo distributed mode, we want to use yarn, and that is what this property indicates. On to the last Hadoop component that requires configuration, the resource negotiator yarn. This we do in yarn-site.xml. No surprises there. There's consistency in how these configuration files are named. Here, we specify the capabilities that you want your MapReduce framework to have. These capabilities need to be monitored and managed by yarn, which is why we specify them in yarn-site.xml. The MapReduce underscore shuffle is a specific feature within MapReduce which allows it to do shuffling and sorting of keys as they flow from the map to the reduce phases. If that didn't make much sense, it doesn't matter. It's a very MapReduce specific feature which you'll understand once you do a course on MapReduce. We can leave it aside for now and just accept this at face value. At this point, we are done with the configuration of Hadoop components and are ready to get them started. But before you start, the first thing to do is to format the name node. The name node is the master node in your cluster. It keeps track of all the other nodes on which processes run. Format this so that we can have a fresh start. Think of the name node as a table of contents for where the data lives within your cluster. Formatting the name node will produce a bunch of messages like this. Make sure there are no errors in the messages. If there are errors, you might have to run the format again or maybe even reinstall and reconfigure Hadoop. Once you're done with the formatting, you can start the master and slave nodes of the distributed file system by calling the command start-dfs.sh. This is in the sbin directory. The messages as a result of this command should indicate that name nodes and data nodes have been started. One thing you might notice here is that we have a whole bunch of warnings which say unable to load native Hadoop library for your platform using built-in Java classes where applicable. This is nothing to worry about. This is because the Hadoop libraries have been built on 32-bit systems. I have a 64-bit system, and this message warns me about that. However, they are perfectly compatible in the case of Hadoop, and you can just ignore this warning. If you want this warning to go away, you need to rebuild your Hadoop on 64-bit, which is possible, but outside of the scope of this course. So just ignore the warnings for now. You've started HDFS. Now we want to double check that the HDFS process is indeed running and the name nodes and data nodes are up. Hadoop provides a special web interface at the port number 50070, especially for the name node. Here you can quickly check whether the name node is active. You have the version of Hadoop running on it, you have cluster ID, and a whole bunch of other things, which is not really interesting right now. Notice though, localhost colon 9000. This is the port where we configured HDFS in the XML files early on. The number of live nodes in this cluster is exactly 1. That's because we're running in pseudo distributed mode. There's a whole lot of other stuff which you might find useful when you're actually debugging Hadoop, when you're a heavy duty user of Hadoop. Here is where the storage directory of the name node is, where it stores the log of what information is present on all the other slave nodes. Before you get started using HDFS, and let's go back to our terminal window once again, create your own directory on HDFS, which will be your home directory. So a user / username directory. My username on this machine happens to be Janani Ravi. And that's the directory that I'm going to create in HDFS. The command to create directory on HDFS is hdfs space dfs dash make dir and then the name of the directory. Notice that the make dir and the name of the directory is very similar to the Unix or Linux commands that you run on your terminal. The only difference is the hdfs space dfs dash prefix. At this point, it's helpful to confirm that HDFS is indeed up and running. All the processes associated with it are up and running. And this you can do by running the JPS command on the terminal. This is a standard command line utility that comes along with the Java JDK, and it shows you the list of Java processes that are running on your system. Note that JPS itself is a Java process, which is why you'll always have that on the list. In addition to JPS, we have name node, data node, and secondary name node. These are the processes associated with HDFS. We learn about what explicitly these processes are. For now, you should know that these 3 processes being up indicates that HDFS is up and running. Now let's go ahead and start yarn, our resource negotiator, which we do by using the sbin / start-yarn.sh command. Check the messages on screen to ensure there are no errors when you start up yarn, and double check that yarn has been started up by running JPS once again. Note that JPS shows that there are 2 additional processes which didn't exist before, the resource manager and the node manager. The resource manager is run on the master node, that is the name node, and the node manager is run on all the slave nodes. Yarn processes have been started up as well. And if you've gotten all the way here, congratulations. You've now set up and run Hadoop on your system in pseudo distributed mode. Hadoop provides some built-in tools to monitor your cluster. The web interface at localhost 8088 gives you a cluster view using the resource manager in Yarn. So just type http localhost 8088 on your screen. This is the cluster view, the web interface for the resource manager, the Yarn resource manager, which manages the entire cluster. Now there's a whole bunch of stuff that's going on here. The first thing to note is at the top right hand side, you have the active nodes in this cluster, which is equal to 1. You can click on the one active node and notice that the node status is running. You have other pieces of information about the node, like the HTTP address to reference this particular node, etc. This cluster view will have much more interesting information once we actually start running MapReduce jobs on it. We'll once again run one of the example MapReduces that's available along with your Hadoop installation. Create the input directory on HDFS. Notice the HDFS space DFS make dir command to create the input directory within your home directory. So /user /Janani Ravi /input. And then copy over the contents of the etc /Hadoop folder onto your input directory. You can list that directory. It'll have all the environment files. You can copy over any files on your local file system into this directory by using the put command that you just saw. And here are the sample files present in the input directory on HDFS, which we'll use to run our MapReduce. The actual MapReduce command is exactly the same which we saw earlier in standalone mode. Hadoop jar, the MapReduce jar which contains the examples, grep, that's the example we want to run, the input directory which contains the files on which the MapReduce will run. Note that this points to HDFS now. It's not on the local file system. That is an important difference when you run Hadoop in pseudo distributed mode. Go ahead, hit enter, and you'll have submitted your first job on pseudo distributed Hadoop install. Notice that the messages are very different here. It gives you a job ID. It'll give you the status of the map and reduce phases. This is because this is now running on an actual cluster. Yes, a single node one, but a real cluster. Now the cluster view at localhost 8088 gets much more interesting. This MapReduce here is the MapReduce that we just submitted on the cluster, and you can see that its current status is running, and you can see how far it has progressed. So you have all the jobs that have ever run in this cluster in reverse chronological order. Going back to the terminal also gives us a status update. It will show you how far the map has progressed. Map is at 57%. Reduce hasn't really moved because map isn't complete yet. Go back to the cluster viewer, click on a bunch of things and see what information you get. Here you'll get information about the specific job, the MapReduce job that we set up. If you open up the link for a particular job, it'll give you information about the specific MapReduce job that we're running. It's an application type MapReduce, it's running, and here are log files for that job. So you can click on logs and see the log files available on the cluster. As I talk about this cluster viewer, I'm only going to hit a few high points, but there are lots of details here, and it's worth your while to spend some time exploring this. Here is the log file, the standard error, standard out, and the system log. Very helpful tools for debugging. As we've been observing this cluster viewer, your MapReduce is steadily progressing in the background. You can hit refresh and get the latest status of the MapReduce. Notice within the MapReduce that we run, there are two individual MapReduce jobs. We did not know this early on, but we can see this in this cluster. And you'll notice this exact same information if you go back to your terminal view. If you scroll up, so our MapReduce job had two individual MapReduces. Both have now run successfully. Check the output on HDFS. Running the cat command on HDFS will show us that yes, indeed, we've got the successful output of our MapReduce. All the words with the prefix DFS and the number of times that they occur in the input files. With this, having successfully set up Hadoop, we come to the end of this module. Hopefully, this module has helped you understand the different install modes available for Hadoop. You're comfortable installing and setting up Hadoop in standalone as well as in the pseudo distributed mode, both test environments.